Good afternoon, everyone, and a very warm welcome to our 2014 graduation ceremony. I would like to extend a special welcome to our guest of honor, Ugo Montanari, Professor of Computer Science, who will be awarded a PhD honoris causa today for his services to both the greater computer science community and to IMT in its startup phase as a professor, PhD coordinator, and deputy director. Thank you very much for joining us here today. I would also like to particularly welcome the families and friends of our graduating PhD students. I hope you are very proud of them on this important day in their academic and professional career. Today's graduates are from the 23rd, 24th, 25th, and 26th PhD cycles, and are made up of many nationalities from around the world, including Germany, Greece, United Kingdom, Lithuania, Macedonia, Serbia and Montenegro, Bulgaria, Albania, Russian Federation, Turkey, Ukraine, Egypt, Cameroon, Iran, South Africa, Pakistan, Uzbekistan, and of course, Italy. They passed at least 3 years studying and living in Lucca at IMT in the full integration between research and education in an international community open to new ideas and contributions. IMT offers, in fact, a multidisciplinary PhD program that integrates scientific competencies of economics, engineering, computer science, physics, mathematics, social sciences, and humanities. Courses are oriented towards the acquisition of research capabilities, knowledge of methodology, and analytical tools. The Institute aims at stimulating participation in research projects in collaboration with the research units and external institutions, and internships within business and institutions, both in Italy and abroad. Since the Institute's foundation in 2005, 279 students have enrolled in PhD programs, and 9 doctoral cycles have been activated. For the 29th cycle, the 2013-2014 academic year, 42 scholarships were granted, for which over 2,000 candidates applied. The number of applications is constantly growing, along with the international scientific community's interest in IMT. In total, 152 students have been awarded a PhD at IMT. At this time, about half of them are working in other universities or research institutes. About 1/4 works for private companies, and 1/4 currently work for other institutions. The focalization of the incoming and outgoing profiles with prospective appointments in mind is one of our missions. Everything that I have just said, however, is just a preamble to pay you, our graduates, a deserved compliment. You are all wonderfully equipped to thrive in this new reality. You have just completed an international education. You know how to get the best out of others from different cultures. Your professors and everyone at the Institute wish you every success and happiness in your lives. And you will always be welcome back. In fact, as alumni, I look forward to our continuing interactions in the years to come. Thank you, graduates, for being part of the IMT community. Congratulations on successfully completing your schooling, and enjoy your graduation ceremony. And I will now leave the floor to Professor Rocco De Nicola for his laudatio in honor of Professor Ugo Montanari.
So, good afternoon, everybody. Of course, I will be very brief, because if I have to start to laudate Professor Montanari for all it deserves, I mean, we will spend all the afternoon here. So I will be really brief, and also because I would like to leave Professor Montanari more room for his lecture, from which I'm sure that we will learn quite a lot. So who is Ugo Montanari? Ugo Montanari got his degree in Milano, in Politecnico di Milano. So maybe, is this working? Yeah. In '66. Then immediately after that, he worked in the States, various universities. After that, he moved to Pisa at CNR. I mean, CNR at that point was really a very, very important institution for computer science. Indeed, computer science started there, and was a sort of a spin-off from CNR that the degree in Scienze dell'Informazione started, and Ugo was one of the first lecturers there, although he was at CNR, he started there. And then Ugo Montanari moved as a full professor at the Dipartimento di Informatica in Pisa, and where, I mean, one of the main things he did was setting up well, was not at the beginning, but established firmly the program in computer science and led it for 8 years. And now it's still a model for most of the computer science in Italy. I would say, for example, the fact that theses were examined outside of Italy and so on now is low. Before, it was not like that in Italy, but Ugo was the first one to set up this kind of program. Was also the head of the department. And the last but not least, I mean, he was also a visiting professor at IMT. In fact, he really helped Pammoli and the others to set up IMT here in Lucca for the part dedicated to computer science and engineering. And really last, but certainly not least, he has just become emeritus professor in recognition of all the service that he did for Pisa University during his, as we saw, really long career, his more than 40 years career. And what are the kind of services that he has done apart of the University of Pisa to the nation as a whole? Well, Montanari had been the coordinator of the Progetto Finalizzato Informatico of CNR. I showed this slide to a collaborator of mine, and he said, was this important? Why you are mentioning it? Yes, it was incredibly important. I mean, the computer science in Italy exists because essentially of this Progetto Finalizzato. There were more than 500 people working, and a lot of I mean, I started working in this Progetto Finalizzato, and the 2 directors of the Institute of CNR, which are in front of us, started working on this Progetto Finalizzato. So that was a really key event for Italy, and part of the merit was for sure of Ugo that was leading an important sub-part of this project. Ugo also co-founded the consortium of Italian universities active in computer science, and then directed it for a while, contributed to the creation of a school in Latin America. Immediately after the democracy in Argentina, there was this need of big changes, and Ugo contributed to founding this school. Has been also the vice chairman of a committee per the Programma Nazionale di Informatica. This was a little bit less successful than the Progetto Finalizzato di Informatica, because on the paper was very, very nice, but then very little was done out of it. Unfortunately, now, not even that. I mean, now we are not even writing programs. Before, we were at least aiming to do something. Now we are even in a position where, I mean, we can try to do something, whatever happens, but we have no finalization of our program. And also, Ugo, I mean, has been a member of review boards of several European institutions, like INRIA, CNR, Swedish Research Council, and so on. He's a member of Accademia Europea, and is a member of the Gruppo 2003 per la ricerca scientifica, which is a group of Italian scientists that have been highly cited, essentially. This is like 30 or 40 Italian scientists are among these. Research topics. What has Ugo been doing? Ugo, also due to his age, probably, but not only, he has worked on a lot of fields. He started, well, I think his thesis was on control theory, nothing to do with our director. Our director was not yet born when Ugo did his master thesis, but his master thesis was in logic control, locus control, the central part of the control. That was the thesis. Then he went to the States and started working on image processing and artificial intelligence, and you will see some topics there. After that, he kind of moved more towards semantics of programming language, because it became clear at that point that it was kind of critical to be sure that the program were doing what you expected. When program were not doing calculations, were doing other things, was more, if they were doing calculation, you could check that the calculation was correct. If there were more things. And so then Ugo moved more toward the sort of semantics and never abandoned that field. So at the beginning, he started to work on logic programming and did an algorithm, unification algorithm, that for a long time was the best algorithm as far as performance were concerned. In fact, and was used quite a lot is in all textbook on logic programming that algorithm is mentioned. Then he was one of the first to start publishing on constraint programming, which is, again, a very, very nice approach to programming, a completely new, actually, new way of programming. And when you talk about soft constraint programming, then it means that you take into account optimization and probabilities. Other work have been on graph transformation, again, as models of programs in order to guarantee their correctness. And one of, maybe most of the last part of his career was dedicated to concurrency theory. And there he has really given important contribution on the semantics of concurrent program, semantics of patternate, and in general, unifying model. Ugo, as you will see from his presentation, has always been interested very much in providing unifying models, so to have a lecture of different phenomenon under a general umbrella. And this has been most of the work that he has done in this concurrency theory. Then some numbers. Ugo has published more than 300 papers. And there, I mean, nowadays, it's not that I give that much importance to the number of citations, but there I measure, anyway, of how the general public receives what one has written. And you could see that the Ugo's paper on constraint programming has written more than 1,200 citations. For those that are not of the field of science, I mean, citations are times that people that write other papers mention the work by colleagues. And then he has written, again, these are kind of seminal papers that really many researchers have taken into account while doing their own work or developing their own work. And Ugo has been listed among the top nurturers. Now, nurturers means somebody that has pupils, and these pupils make career in science as well. And okay, so Ugo had 20 PhD students plus other pupils. I mean, and I consider myself another pupil, not a PhD student, because I did my master thesis with Ugo. And it's very nice that there are few others pupils here that did the master thesis with Ugo. They are still here. So there is this strong connection with Ugo, although he was not even our professor. I mean, but we still call him our professor. And as I was saying there, I mean, in 2014, he was the 7th worldwide as a nurturer, which means him and his school in number of citations, essentially. This could be said in brief. And this is a picture, I mean, of the kind of collaboration that Ugo has, but is only, I mean, this graph was too big in order to be really reporting. No, these are only the main collaborators. Some faces are also, again, in this room. I mean. And I would just like to conclude with the word by another collaborator. It's our past director that felt that was important anyway to say something about Ugo. This is written in Italian, but I mean, it's Fabio Pammolli that worked with Ugo here in IMT to start with IMT, essentially, and he says that really has been an honor for IMT in the starting phase. It has been really a pleasure to collaborate with Ugo in both as chair of the computer science PhD program and as vice director. And I think it is a good way to conclude my presentation and leave the scene to Ugo. And so I would like to invite Professor Montanari to give his Lectio Magistralis. And he will talk about why sometimes abstract models are more practical. questo.
Okay, Rocco, thank you very much. Alberto, thank you very much also for your kind words. Well, I have really to say that I'm very glad to be here, and that the kind of work that I did for IMT was able to develop and to help developing such a nice institution which has already achieved a lot of results. The kind of thing that I will going to tell you today is strictly related, of course, with my experience and in part with what Rocco was mentioning before. So I will start from my personal experience, and my line of development was mainly from practice to theory, and at some extent also back. And therefore, I will start just to give you an idea, show some pictures which have to do with my first part of the theory, which is of my life, which is, of course, what is easier to show since they are pictures. So one of the first things that I did has to do with skeletons, which is a way to find the center of axis of a picture, in this particular case of a chromosome. And this is, the mechanism is essentially propagation, which is also analogous to other techniques which are called computational fields, which are used today for a lot of different purposes. Instead, this second picture that I show you is a way to recognize within a noisy picture a line that you had before. This, in fact, was in the cover of an issue of the communication of the ACM long time ago. And the idea is that you pick up the line that you have here on the left. You put a lot of noise, and this is the kind of picture that you get. And still the algorithm will find the best possible line in the whole picture, recognizes something which is very close to the original one. Even if looking here, it's very difficult to recognize anything just by looking. So another kind of work that I did is so-called hidden line elimination. You pick up a piece of solid, typically a piece of architecture, and you draw by canceling lines which are behind the front of the view. This is completely classical. My algorithm was the first published. For a lot of time, it was compared with other algorithms which have been proposed in a convenient way. And this was a reasonable piece of code, because at that time, of course, there was nothing available. In particular, list structures were not there, while instead here everything is done with list structures, which were just controlled by the programmer. This is another one. Another example is the Barcelona pavilion by Miss van der Rohe. And here you have some of the pictures of the reality, and this you have some examples. The last one that I'm showing you is an optimal matching of chromosomes. You have a view of parameters of chromosomes, and you have to try to match the closer ones. And this is done via an algorithm which is called A-star, which is an artificial intelligence algorithm close to branch and bound to do the optimal matching. Okay, so what I did is then to move to theoretical areas. And the area that I was actually working most of the time was concurrent and distributed models of computations. And in particular, as Rocco mentioned it before, my main interest was to try to develop meta-models, models which are encompassing a variety of different cases. And one of the tools that I used to do this kind of work was category theory. So then, more recently, I tried to go back to some more practical matter, like games for grid scheduling, reinforcement learning, optimal profiling for smart power grids, and e-mobility, which are very recent activity. Now there is the need to try to embed the theoretical results all the time within practical applications. Okay, so why metamodels? The idea is that metamodels yield a most useful theory because they try to explain concepts in a general uniform way and help better design from the point of view of the engineering approach, because they force you to have an inductive process for defining the metamodel and the deductive process for checking soundness and generality of the metamodel. Here I will present some comments based on my experience on particular classes. Of course, I will not be technical, and this, of course, will make a little bit more difficult to understand what is the research aspects of the issue, but I hope to be able to give you at least a general idea about several cases. Okay, so the roadmap of the talk that I am trying to give is, first of all, trying to see the way in which computer science works in front of the natural phenomena, and what is the role of abstract model in modeling the role of computer science. And these abstract models must be modular and parametric. And then I will consider in a number of cases concurrency, networks, transition systems, constraints, where this kind of abstraction, as in the past, worked very successful, and for which I, especially thanks to the people that were my students and worked with me and were PhD, as Rocco was mentioned, actually were able to develop. Okay, so I will start with the first issue. So natural sciences discover phenomena, guess, and check laws. Mathematics looks for deep results guided by originality and formalization of rational concepts. So you have very different roles between natural sciences and mathematics. Computer science is a little bit in the middle because both studies natural phenomena and develops design goals. So you need to study the main concept and also to develop design methods. So from that point of view, computer science is a little bit in the middle between natural science, mathematics, and also engineering. The natural phenomena in computer science that I was considering are very general. There are a number of natural limits to computers and computation processes, which have to do with very general results. Typically, you have computability. You cannot compute something which is not computable. You have issues of algorithmic security. You have limitations which is due to algorithmic complexity. You have a limitation which are due to the fact that you need security. In physics of circuits, you have limitations on how detailed is the kind of lithography that you do in printed circuits. You have limitation on the clock frequency that you can use for those particular circuits. And if you try to execute algorithm in a concurrent way, in a parallel way, then you have limitations which have really to do on the intrinsic amount of concurrency that you have in the problem. So those are, let's say, natural in a slightly different sense than looking at bacteria, but they are still natural phenomena. Then you have a number of issues which have to do with natural phenomena which occur in unplanned large global systems. And here, of course, I can mention internet and WWW, but also a lot of other things that are going to change the structure of society: service-oriented computing, hybrid cyber-physical systems, big systems which keep to be more and more controlled by computers, social network, of course, everybody knows. So it's interesting to see that there are certain things which are natural, certain other things which in a sense are still natural because they have not been designed. They are not the result of a planning operation from the human beings. So one of the important issues then is modular design process in computer science. The idea is that whenever you have a big object, you have really to break it down into pieces, divide et impera, in order to be able to make an engineering design which is acceptable. In the case of computer science, you have, if you want, two notions, one vertical and one horizontal. The vertical decomposition is that you have layers of virtual machine that go from the machine to networks, to overlay networks, where they work one on top of the other. The other is that instead you have an horizontal modularization for usability flexibility. Let's be a little bit more detailed. In the case, for instance, of the layers of virtual machines, the most classical fact, which is there from the beginning, from von Neumann 1945, is the fact that you have a machine language which separates the realm where you have continuous electrical phenomena and a situation where you have instead discrete steps, like, for instance, a buffer assignment. So this is a separation between two worlds which are completely different and for which different improvements have been produced in the years in a rather independent way. And then on top of that, you have a variety of layers like that, where you have operating system, middleware, hypervisor, available virtual machines of all kinds. And again, the main point is that you have an interface such that you can change one side or the other side without having to change everything. So you can make your system better and better just by changing pieces and still hoping, most of the cases actually being, the whole system being able to produce, to keep working fine. Then you have modular programming languages. Programming languages nowadays have all kinds of modular structure which offer environments for different classes of applications, and you have libraries for use. So in this is what I called horizontal modeling, because you have libraries and you have different programs that can be combined to produce a variety of applications. So if the way in which you decompose computing system is so structured, also the models and your formal definition of what is the interface between a part and the other must also be modular and parametric. So the basic point is that you have a lot of virtual machine connectors and interfaces. How those are specified? How is this a mathematical modeling or engineering design? How it might happen that all these parts, which are in principle separately designed, work together? Well, it's the issue of mathematical modeling of engineering design. Well, mainly from engineering design, at least at the beginning. But nowadays, since systems become more complex, global, and heterogeneous, it's fundamental to have formal specifications to define in a precise way the interfaces between all the different parts of the system. Okay? So, in order to be able to do this modeling, you must have a formal definition which themselves should be flexible, modular, hierarchical. You want to have models which are concise and parametric, and they should capture all the similar instances of the concept. This is typically of science, the fact that you try to get the most general notion of a concept that you designed, that you developed. But it's also fundamental in the design process in computer science. In fact, I would say that if there is one thing which is typical of computer science with respect to engineers, is that the engineers tend to try to capture and to understand the whole thing, while computer science tend to tell me, but what is the interface? What you look at? I'm not interested in what is under it. I'm only interested to what I see of what is under it. Okay, so now we are talking then not of parametricity and modularity of systems, but parametricity and modularity of models, which are fundamental if we want to use the models to represent the effect on the system. The seminal work in this area has been done by Rod Barsal and Joe Gauguin, which in a very famous paper in an International Joint Conference on Artificial Intelligence of '77, published a paper called Putting Theories Together. And first of all, it might be surprising that this was done in an artificial intelligence conference, but at that time, a lot of the interesting issues in theoretical computer science happened in artificial intelligence area, including the most, let's say, important issues of type theory. What was there? There were so-called Lowire algebraic theory and functional models, functorial models, which means that you have a general way of representing algebras in the sense of their syntax, their semantics, and more interestingly, the way in which you can combine, parameterize, and extend. So this is the idea of the putting theories together. So you have several ways of defining various pieces of theories, and you have mechanisms which allow systematic methods to put them together and to derive all the conclusions. Later on, a little bit later, 91, I mean, it started before, but 91 was the point where the whole theory was general, is this notion of institution, which is the most general notion of where you have generic ways for combining different theories. And this has been very interesting in what follows, because not only the way stayed at the level of theory, institutions are really just logic, but also arrive to efficient implementation of systems which are actually able to develop the theory and to combine them. So, providing efficient implementation, animation, and metaprogramming. The most famous was the OBJ family, which was derived by Joe Gauguin, Jose Meseguer, Claude Kirchner, and Kokichi Futatsuji. And so this is one generation. Another generation was rewriting logic with mode. And mode in particular is very widely used, for instance, here at IMT within a real project called Athens. So you see here an example. We're starting from a seminar work and going through something very theoretical, arrive to something very much of practical use in trying to combine a model and define the models of computation. Those are the two people. This is Rod Barsal, and this is Joe Gauguin. Rod Barsal is still alive. Joe Gauguin passed away maybe 10 years ago. Joe Gauguin was a mathematician worked most of the time with IBM and then University of California, San Diego, while instead Rod Barsal is from Edinburgh University. Okay, now I will try to tell you some details about a few interesting cases, at least from my point of view. Here, of course, I am referring to my experience. And as I said, I will talk about 4 items: concurrency, networks, transition system, and constraints. So, what is concurrency? What is theory of concurrency? Well, the main thing about concurrency is that in your model, instead of having separate computations, you have just equivalence class of computations, which are called concurrent computations. Those are computations which are independent from the order in which you sequentialize concurrent events. So you have a notion of concurrent event, which has to do, of course, with the model. And then all the linearizations, all the way in which you exchange different concurrent events is considered to produce the same computation. And therefore, your semantics, your effect, your applications must be independent of the order in which those events take place. In particular, this means that the implementation is free to choose one of the possible, or if you prefer, the most convenient in that particular moment about the way in which you can execute all the events. So this allows you to work with different speeds, and the fact that you can have a behavior which is independent of the different speed of the various processes is absolutely essential. Imagine, and in fact, sometimes you have to do it if you are real time, but in most of the applications, you don't care. Otherwise, in particular, the effect could be different according to how fast is the user to press the button. And this cannot be the case. Or you can have completely different software according if you change one particular processor from the previous to the next generation, because your software does not work anymore because the speed will be different. Okay, so this is a good example of how concurrency comes from a theoretical point of view, but then as a very practical notion, different speeds are possible, and it's essential for program reuse. Now, from the theoretical point of view, the issue is how to define equivalence of computations. And technically, this was done using a particular notion called monoidal categories. And it's interesting that this construction in terms of monoidal category is essentially the same for all kinds of model of computation which has to do with concurrency. You can think of 10 of them. And in all of them, when you introduce at the right point this notion of monoidal category, then you obtain what you want. And the first time this use of monoidal category appeared is in a paper by José Meseguer and myself. And one very nice modern presentation of this written in Italian is in a book by Einaudi, Pensare il Mondo, by Roberto Bruni and myself. Another related point is that of causality. You can think that if two things are not concurrent and they are not excluded, in other words, both of them can happen, then you have a notion of causality. This notion of causality is essential in a lot of cases, in a lot of the approaches, to represent correctly non-interference, which is an important notion in security. Because if you have the two events are not causally related, then there cannot be any transfer of information from one to the other. So, thousands of different approaches have been done for non-interference. Most of them actually use this basic concept, and therefore have to present a different model of computation where the notion of causality is exploited. Okay, this I'm not sure if you know him. If you know him, and this is the laurea degree by Rocco De Nicola. This was one of the main person that we worked, not this particular paper, but later on when Rocco came back from Edinburgh with the PhD by Matthew Hennessy, his work, then we kept working together for a long time, and we have Degano De Nicola Montanari, who wrote several papers, and some of them are still mentioned by a lot of people. Another person is Ilaria Castellani, one of the first that we worked at, and she's now in INRIA Sofia Antipolis. And another one is Roberto Gorieri. He's now professor in Bologna. Just a few of the people that worked on this issue about concurrency. This is instead José Meseguer, the main, let's say, co-author of the main paper that we had before. He's at the moment professor in Urbana-Champaign, University of Illinois in Urbana-Champaign. He's in the middle of some mountain, you see, you hardly see some lakes, some snow under it. He likes very much to. And then it disappears, so there is no way to reach him with any email or any other way. Okay, so another example is networks. So if you have, if you want to have all kind of networks, and typically, if you take a distributed system, you could have the need to interface hardware and software components or to build communication network. In a lot of these cases, you will have the need to define an abstract notion of network and through the network what you want to go. You want to have messages, you want to have, so in most of the cases, the natural way to represent the network is in terms of a graph model of computation. And then the graph may correspond to a connector network, so you have components and you have connectors. It could be a neural network, which is a particular kind of network from this point of view. And you might have network where you want to express at the same time concurrency and non-determinism. And also would like to be those kind of network to be compositional, to be able to compose them together, but still being able to predict their behavior. In this line, we developed some notion of connector algebra that were very general, together with, again, Roberto Bruni and Pavel Sobocinski, who is now at University of Southampton. And this connector algebra are, in a sense, universal, in the sense that you can express through them all kind of interactions. And in particular, some extensions in terms of Frobenius algebras can be used in a very interesting way to study pure quantum states and operations on them. The kind of connections that you have in different states which are dependent, which are entangled, can be represented in a natural way using this kind of connector algebras. Let me go now to transition systems. The transition system is the most natural operational model because, roughly speaking, a transition system is a graph where nodes are states and transitions are moves from state to state. However, the transitions are labeled, transitional states, but typically transitions are labeled, and the labels that you have on the transitions are the observable behavior of that particular transition. And these labels can contain all kinds of information. It can be just actions or time constraints or probabilities or all kinds of quantitative parameters. And the behavioral properties that you can represent with this labeled transition system are typically modeled by temporal logic, and temporal logic gives a property which, if you are able to model all the states of your system with a single labeled transition system, which can maybe even be billion of states, then you can check in real time a particular formula, if a particular formula holds, using techniques of model checking. This is the most used formal techniques in present day for computation models, and one of the things that you could do in addition to checking temporal logic is to look at the equivalence between states and systems, and as a result to define a minimal automaton where you identify all the states which are equivalent. Once you have a minimal automaton, you typically have a easier to handle model on which you can check all kind of properties. One of the very interesting properties that you have, very interesting features that you have in these systems, is that you have quite often what is called a logic adequate. The idea is that you have on one side two systems, and on the other side a property. And you have the fact that the two systems are equivalent if they satisfy exactly the same set of formulas, the same set of properties. And if you turn the things around, they are different if there exists a formula which differentiates between them. So this is very nice because you have a counterexample which show why the two systems are not equivalent. This is, again, very general property. So we are still in a situation where we have a variety of situations which are interesting enough, but where you do not know which one, because it happens that thousands of notions of temporal logic and observational equivalence have been defined in practice. So what you do at this point? Well, you can choose one of them, but it's very difficult to see the one of them, because not by chance several of them have been developed. They've been developed for different applications, for different systems, for different characteristics. So how you try to unify the theory? Well, what actually happened in this particular case is that you have a categorical notion of coalgebra, and B-algebra is a variation, where you have a unique concept of bisimilarity and modal temporal logic. So the notion of bisimilarity allows you to see when two states are equivalent, when two systems are equivalent, and how to minimize the automaton or the model. And on the other side, the modal temporal logic gives a class of formulas for which the adequacy property holds. So how it happens that you have a unique notion from the categorical point of view and thousands of notions which have been proposed? Well, you can actually achieve the match by choosing the base category and the behavior functor, which are two variations, two parameters that you have in the categorical construction. But this makes life much simpler, because you can see what is the structure where you live in, which is the underlying base category, and what are the transition system in your system, and this is specified by the behavior functor. So this is an ongoing work, and I would like to say that this is really a very successful story, for category. A particular case of interesting is where you have models of computation, where you have names. Those are called nominal calculi, and the names are used for representing communication channels, links, keywords, session identifiers, passwords, all kinds of items of this sort. And if you have this ability of generating new names, links, keywords, and so on, typically your transition system becomes infinite, because it's enough that you have a cycle where you generate a new name that immediately you can generate an infinite number of states, and therefore you cannot use model checking, which was so convenient. However, it is possible to use certain techniques which allow you to have a finite model also in that particular case. And this finite model was defined some time ago and was called history-dependent automata. Several people actually worked on that. Here I have a couple of pictures. This is Filippo Bonchi, who is now professor at École Normale de Lyon. Instead, this is Vincenzo Ciancia, which instead did CNR. I'm sure that some of the present people know him, or at least have seen him. This is Matteo Sammartino, who just finished last December the work. And all of them worked in different aspects of this history-dependent automata. Let me go to the last of the items. And this is constraints. And so the idea is that constraint systems are widely used concepts that have very different formal meanings, both in philosophy or in literature or whatever you want, not only in computer science. But the simplest version is what is called network of constraints. And a network of constraints is a very simple model. It's essentially an hypergraph. So you have a graph where instead of having just arcs, you have arcs with more than 2 connecting points. And the nodes are supposed to be variables, and hyperarcs are constraints, in other words, predicates, in other words, set of relations, sets of tuples, the relations. So they are constraints which must be satisfied by the addition variables. If I have an arc with 3 connecting points, and therefore it is connected to 3 nodes, then it means that it restricts the possible values of the 3 variables. Only certain triples will be allowed. So the arc will represent a relation between the possible values of the 3 variables. Usually, you have a finite set of possible values for the variable, so the whole thing is finite. And the typical problem that you have is to find assignment of the variable which satisfy all the constraints. However, this problem is very difficult. It's NP complete. In other words, you cannot hope to have, in general, an exact, good solution in any polynomial, in polynomial time. It's supposed to be exponential. Nobody actually proved that it must be exponential, but this is what everybody expects. But still, you can have efficient algorithm in special cases. You can decompose your graph into small components, and in that case, if you are lucky in this way, you can use a linear dynamic programming algorithm, which essentially corresponds to build a tree of logical clauses and solving each of the clauses one after the other. And then you have approximate solution via propagation relaxation. So, an interesting extension of the classical theory of constraints, which was developed at the beginning of the 70s, is using so-called soft constraints. Here you have, instead of just a yes or no, so a constraint either is true, either or not, either it is satisfied or not, you have a degree of validity or a cost or a set of cases in which a constraint holds, in which the solution, the problem has solution. And these various options can be possibly composed using operations which are generalization of the sum and product of logic booleans. So, in terms of the structure that you need, it was developed a notion of constraint semi-ring, and a constraint semi-ring is just a semi-ring where you have that the addition is idempotent and the multiplication is commutative. And you can include as a constraint semi-ring a lot of different models, typically the logical, the fuzzy, the tropical semi-ring, which means optimization, mean and sum. And one of the interesting properties of constraint semi-rings is that the Cartesian product of constraint semi-rings is still a constraint semi-ring. And a functional domain built on top of constraint semi-ring is still a constraint semi-ring. A power domain, a Hor power domain, which has to do with the fact that you have a multi-criteria optimization, Pareto optimization, can also be made on top of constraint semi-ring and still obtaining constraint semi-ring. So this again means that general techniques that you can use for solving or handling constraint semi-ring can be applied at different levels without problems. One of the most interesting things that could happen is that the functional domains can be used to internalize variables. In other words, the variables that we had before as nodes of the network of constraints can now enter directly in the structure of the semi-ring, and therefore, by making the operations on the semi-ring, you are also able to compose networks of constraints. In fact, what happens is now that now constraints are not true or false or anything like that, but they are functions which assign logical or soft values to variable assignments. And this is very similar to what you get using set of clauses once you have an object interpretation of some product and restriction. So in this way, we build a connection between something which is in principle very simple, which is network of constraints using logical, something where instead we have network of constraints using more complex structure, for instance, for optimization, and the fact that instead you have recursive clauses, Herbrand constraint system. So in this way, you are able to connect what happens for the constraint semi-ring to what happens in something which in principle is very different, which is data log, logic programming, constraint logic programming. In all of these cases, you can play the game of getting soft. In other words, instead of just saying if a particular goal of logic programming holds or not, you can tell me what is the cost of this particular value. Not yes or no, but a cost associated to that. Okay, so we did it with several people. The first one is Francesca Rossi, who is now a professor in Padova. Stefano Pistarelli, who is here, is now professor in Perugia. And one of the interesting ways in which the constraints can be used and are used recently is trying to use constraints to represent knowledge, and then to combine constraints with processes, with service, and with other paradigms like contract or session paradigm. And this is, this way you obtain a new class of models of computation which are called concurrent constraint programming, and in particular one of them, which was recently developed essentially here at IMT, but people working here at IMT, is in concurrent constraint related to the so-called pi calculus, which I'm not going to explain. And one of the interesting issues that you can try to solve by having this interaction between constraint as a way to represent knowledge and the process-oriented version to represent execution is that you try to combine declarative and procedural aspects within the same system. I will mention here a particular case, which is the language CEL, which means Service Component Ensemble Languages, which has been developed in a project Athens, where both the group of Rocco here at IMT and my group in Pisa actually collaborates, where it is possible to have abstractions that allow one to represent directly behavior and knowledge aggregations according to specific policy. So you have a generic mechanism again, but this time at the level of a language, which will try to put together two very different things. On one side, knowledge, on the other, behavior, trying to combine them in the most general and flexible and expressive way. In terms of the CCPI, this was done with Marzia Buscemi, who is also, she's also here. She is not anymore working on the subject. Then I have some just conclusions. My point of view is that metamodels are very useful because in theory they try to exploit the essential concept and therefore try to find the best way to express the relations and the connection between different concepts. While in practice, they can help in developing modeling tools, verification, simulation, and animation, which apply to a class of different notions. The issue has to do with the underlying theoretical computer science and mathematics, which involve typically category theory, logic, and probability, and also the way in which you work towards implementation. And this has to do with software engineering and theory of algorithm in order to try to make the various steps also efficient and not only mathematically simple. That's it. Thank you very much. Resta in piedi. Aspetta che faccio. Forse te la devo dare a te questa qui.
So for his seminal and pioneering contributions and insights in image processing and artificial intelligence, in logic and constraint programming, and in concurrency theory. For his exceptional continued role as a nurturer and mentor, for his services to both the greater computer science community and to IMT in its startup phase as a professor, PhD coordinator, and vice director. Upon recommendation of the Executive and Academic Councils and by authority of the Ministry of Education of the Italian government, I hereby confer upon you the degree of Doctor of Philosophy honoris causa in Computer Science and Engineering. Congratulations. I would now like to congratulate all of our graduates on their achievements and wish them every success for the future. I invite them to come to the podium to get their diplomas. So the first one is Davide Giadanini. Political Systems and Institutional Change for his PhD thesis in Common Sense and National Emergency, Neoliberal Hegemony in the 90s Italy.
Grazie. Facciamo una foto. Vengo così? Sì, tutti e due?
Sì. No, non importa fare tutte. Ci stiamo due. Next, Emanuele Caellini, Computer Science and Engineering, for his thesis in Combining Peer-to-Peer and Cloud Computing for Large-Scale Online Games. Congratulations. Then Lorenzo Cicchi, Political Systems and Institutional Change, for the thesis on the logic of voting behavior in the European Parliament, new insights on party group membership and national affiliation as determinants of vote. Then Carlo Giuseppe Ciulli, Political Systems and Institutional Change. The title is in Italian, La sinistra italiana e il processo di integrazione europea, la transizione del PCI attraverso il suo discorso sull'Europa. Then Adele Del Sordi, Political Systems and Institutional Change. PhD is on the Party of Power of Kazakhstan, the origins, resources, and regime supporting functions of Nur-Otan. Next, Evinch Dogan, Management and Development of Cultural Heritage. The thesis is on analyzing the impact of mega event on city image by visual methodologies, branding Istanbul during the European Capital of Culture 2010. Then Alberto Fogerio, Management and Development of Cultural Heritage. The thesis is on the underwater cultural heritage, a comparative analysis of international perspectives, laws, and methods of management. Simona Losito, Political Systems and Institutional Change, the Human Rights Diplomacy, the Carter Presidency, and the Relationship with Brazil, 1977-1981. Then Irina Miakina, Political Systems and Institutional Change, the interplay between bureaucracy and globalization. Mike Modica, Economics, Markets and Institutions. The thesis is on essays in regional and complex urban economics. Leopoldo Mondauto, Economics, Markets and Institutions. The use of administrative data from the evaluation of the EPL effect to the analysis of the university graduates' labor market. Francesca Pampaloni, Computer Science and Engineering, Quantitative Models of Information Flow, Tuning the Power of the Adversary. Michael Helklitz, Economics, Markets and Institutions, 2 essays on institutions and the state in Russia and the study of absorptive capacity. Farshad Shams, Computer Science and Engineering, Cooperative Techniques in Wireless Communications, a Game and Information Theoretic Analysis. Definitions. Next one, Ahmed Assem Shams Eldin, Management and Development of Cultural Heritage. The title of the thesis is Human Occupation Development in the High Mountains of Sinai Peninsula, Egypt, with alpine and Himalayan reflection in the light of rural-urban development, socioeconomy, semi-arid watershed management, socioecology, and land-use policy governance. Hope the thesis is not as long as the title.
I try to shorten it.
Next one, Alain Chowkam Siwe, Computer Science and Engineering, Prosumer Planning in the Descent Context of Regenerative Power Production. Congratulations. And the last one is Andoya Van Dien, Computer Science and Engineering, Specification and Analysis of Systems with Dynamic Structure, System with Dynamic Structure. No, that's a typo. Specification and Analysis of System with Dynamic Structure. Okay, I think we are finished for today. Thanks everybody for attending.